So let's discuss as to how we can evaluate the Fourier transform of such type of a triangular signal. So we can also represent this triangular signal. Mathematically, can take a representation and we say that we will write triangular signal for such signal, and its height is a, and it is symmetric around 0. So any symmetrical signal around this 0 with this point as minus r and this point as plus r and height as a, we represent by this. So our objective is to evaluate Fourier transform of such signals. So for this, we would use a trick that says that Fourier transform of rectangular signals of type this is known to us, and we know that convolution of two rectangular pulses with same width provide you a triangular pulse, provides us a triangular pulse. So we'll use this fact in order to evaluate the Fourier transform of these triangular signals, and this is how we represent this in mathematically, and this is graphical representation of such triangular signals. So let's use the second fact first, that the convolution of rectangular pulse rectangular pulse, let's say the height is b, with this pulse, with the same pulse as I told you that the convolution of the rectangular pulse of same width but height might be different. So let us say the height is this, and for such a signals the or just take the same height. Why it make things complicated? So for the same rectangular signal, the convolution of this signal okay, let's take the general case. The height of this is c. The height of this signal is c. Convolution of these two is a triangular signal. A triangular signal. And the support of this will be from minus 2r1 to 2r1. And this value will be b into c 2bc into r. You can just evaluate the convolution of these two signals. If this is x1t, this is x2t, and this is your yt. So from our previous discussions, you can see from my previous lectures, and link I will provide you, you can find out that the convolution of these two signals will be this. So if I represent this rectangular signal like this, minus r1 comma r1 at p, this rectangular signal as this. The convolution of these two will give me a triangular signal, and if you remember that we use this notation for such a triangular signal. So we can write this triangular signal as so we know that the convolution of these two rectangular pulses is this triangular pulse. So let's write a new slide, that rectangular signal of this, not A, it's B, convolved with another rectangular signal of the same width, and the height support must be same, but the height might be different, will give you a triangular signal or triangular signal of minus 2R1, 2R1 and C. So next our aim is to find out the Fourier transform of this signal, right? The aim is to find the Fourier transform of this triangular signal. So let us first try to find out the Fourier transform of this triangular signal, and then we will just replace the value of R1 with the corresponding R's. So we know that Fourier transform in time domain is nothing but multiplication in frequency domain, right? So you can write that Fourier transform of this is same as Fourier transform. That Fourier transform is the convolution of two signals, same as the Fourier transform of first signal multiplied with the Fourier transform of the second signal. So this will give you the Fourier transform of this triangular signal. And this is what we want to evaluate. And this is simple, that we know that and if you remember that Fourier transform of any such signal, Fourier transform of this signal is 2BR1 sinc of 2R1 into. So Fourier transform of such signal, you can remember this using this trick, that this is nothing but the area of rectangular pulse. You want to evaluate Fourier transform of this pulse, this will be area of the rectangular pulse. If you try to see the area of the rectangular pulse is 2BR1, and this is the width of the rectangle. So the Fourier transform of a rectangular pulse is this. And here, if you just try to equivalently plot this signal is this minus R1 into B, and Fourier transform of this signal is minus R1 to C. So by using this logic, or this theorem, you can say this theorem, or this result, by using this result here, we can write that this is 2BR1 Sinc of 2R1 f, this is the Fourier transform of this, multiplied with the Fourier transform of this, and this will give you the Fourier transform of this pulse. So the Fourier transform of this pulse is this. So let's this result which we have obtained, that Fourier transform Fourier transform this pulse is 2, if you just multiply 2VR1 with 2CR1, for BCR1 square sinc square 2R1 into F. And our objective was, what was the question? We wanted to derive the Fourier transform of this pulse. We wanted to derive the Fourier transform of this pulse. So we have to just accordingly set these parameters. So we have to write 2R1. We have to replace in this using in this result. This result we have, and we want to derive the Fourier transform of triangular pulse. So we have to write 2R1 as R and 2BCR1 as A. So for this we have to replace R1 by R by 2, and we have to replace BC by A by 2 R1, or 2R1 is R, A by R. So we have to replace BC by A by R, and we have to replace R1 by R by 2. So you can do it here only. So our final result will be that the Fourier transform of this, okay, let's write in the next slide, that the Fourier transform of this signal will come out as BC replaced by A by R, so A by R, R1 is R by 2, R by 2 into R by 2, sinc square two into R1 into F, R1 is R by 2. So you will get AR sinc square R. So Fourier transform of this type of a triangular pulse can be evaluated using the concept developed here, and this is the sinc square function. This is also called, we generally see that the Fourier transform of a triangular pulse is sinc square. Just please check if there is any calculation mistakes, that let me know, but I think all is well. So this is how we will evaluate the Fourier transform of a triangular